Hello again. Next section is called Properties of Logarithms. Again, this is a review section, so I'm going to list some of the properties that you guys have seen before, and then I'll do a few examples and some application problems. So let's start with the properties. And again, these are kind of like exponents, so this is how you can remember them. If you have the log and any base of a product, or if you have the log of any base of a quotient, or if you have the log and any base, so right now I'm using base b for all of these, and x times y, x over y, or let's say x to the n. Okay, these are the three main log properties, and maybe you remember them, maybe you don't, but in case you forgot, when you are multiplying, you add. Sounds familiar, right? So this would be the same as log base b of x plus log base b of y. When you are dividing, you subtract. So this is log base b of x minus log base b of y. When you are doing a power, you multiply. So what's going to happen is this n goes in front of the log, so it's n times the log base b of x. Okay, so these are the three main properties that we've talked about, well, you guys talked about in Algebra 2. Alright, so now here are some examples using these. Okay, so there are two kinds of problems. One of them is condensing, which means we're going to take things that look like this, a sum or a difference of logs, and we're going to try to go back this direction and write them as one single log with just a coefficient of 1. The other one is called expanding. We'll talk about those in a couple minutes, but it's basically starting with one log and then writing them as several logs, a sum or a difference. Okay, so let's say we want to do some condensing examples. A typical example would be something like, let's say I have log base 7 of x squared plus log base 7 of y squared. Let's say we're subtracting log base 7 of x cubed, and we're also subtracting log base 7 of z. Okay, so the way I look at this, when you're condensing, you're going to try to squish them into one log. So it's log base 7 of something. So all four of the logs that you see here are going to combine to give you one argument. And based on these properties, I see that basically any log that's positive, the argument in this case, which is x or y, is in the numerator. Here, the log that's positive, the argument goes to the numerator. The only time we have anything in the denominator is if there's a negative in front of the log. So the way I'm thinking about this problem here is I see that we have four things. X squared, y squared, x cubed, and z all need to go inside of this log. Since we are adding these first two logs, the arguments, which are x squared and y squared, go into the numerator. And since I'm subtracting both log base 7 of x cubed and log base 7 of z, the arguments, which are x cubed and z, those go to the denominator, because we want to divide by those. And then now all we do is simplify if we can. So here you see that we have x squared on top, x cubed on the bottom. You can just make that 1 of x on the bottom, and then y squared on top is good, and the z on the bottom stays. So this would be the final answer for this problem. So we started with a whole bunch of logs, and then we condensed it into one final log. One more condensing example. Let's say we have something like log base a of, let's say, 9 minus log base A of 81 plus log base A of A, let's say minus log base A of 7. Okay, so again we have several logs here. If we're going to make them into one, it's going to be log base A. The 9 came from a positive log, so that goes in the numerator. This A also came from a positive log. And then now we also have two negative logs, so those are going to go to the denominator, 81, 7. So then this becomes log base A. We can simplify 9 over 81, so it's just 9 on the denominator. So then this is going to be log base A of A over 63. Okay, so that's some basic condensing examples. Now, if we want to do some examples of expanding, we're just going to go the other direction. So again, this is writing as a sum or difference of logs. Writing them in as many logs as possible. Let's say we have something like log base 5 of x, y, z squared keep it easy to start. Okay, so if we're expanding something like this, I see 1, 2, 3 things that we're multiplying in the argument here. So that's going to translate to 3 separate logs. Log base 5 of x, and since this is all multiplication, we're just going to add all 3 logs together. So log base 5 of x plus log base 5 of y plus log base 5 of z squared. Okay? Now the last thing that we can do we can put this 2 in front of the last log. So it would be log base 5 of x plus log base 5 of y plus 2 log base 5 of z. Okay, so when you expand, you write them in as many logs as possible, and we usually don't want any products, quotients, or powers in the argument. Okay? Let's do one more expanding example. So let's say we have, let's do a natural log problem. Natural log of, let's say, x cubed plus 8 all over x squared y squared. So here we have a log of a quotient. So right now I'm thinking we can do the log of x cubed plus 8. This is one term. It's not 2 separate logs. There's no property that says an addition in the argument becomes something else. Okay, so we keep this together. But we are dividing by x squared and y squared, so we could say, let's subtract ln of x squared. And we also want to subtract, since we're dividing by y squared, we want to subtract natural log of y squared. Okay, so then this becomes natural log of, since we can factor x cubed plus 8, we can keep expanding, we can keep writing this as more, so this will be using the difference of cubes form, or the sum of cubes formula, This is the same as the natural log of x plus 2 times x squared plus 2x plus 4. Oops, sorry. This should be a minus right here. X squared minus 2x plus 4. The other logs are good, except that we can also now bring in these powers out in front. So then this becomes natural log of, and since here we are multiplying two things, this x plus 2 times this x squared minus 2x plus 4, this becomes two more logs. So natural log of x plus 2, multiplication means addition. So natural log of x squared minus 2x plus 4, and then minus 2 log x minus 2 log y. Okay? And if it gets a little weird with the way that you write log, sometimes I make my L's cursive, but you can put parentheses around this so it doesn't look like 21 or something silly like that. Okay, so there's examples of condensing and expanding. Let's try one kind of application problem. Let's say we, for instance, let's say we know that the log base a of 3, let's say that equals 1.1. Let's say log base a of 5, let's say that equals 1.3. So let's say that we're given this information and we want to find, let's say, log base a of 75. We'll do a few of these. Let's say we want to find log base a of 9 over 5. We'll do one more. Log base a of, let's do 125a. Okay, so the idea behind these kinds of questions, if they tell us some information about what kind of logs we have and what those equal, since we don't know what log base a of 75 is, or 9/5 or 125a is, what we want to try to do is, so let me do the solution for a here. We want to try to split up 75 using the numbers that we are given, like 3 and 5. So since I know 75 is the same as, let's see, 25 times 3, I'm going to say that log base a of 75 is the same as log base a of 25 times 3. I haven't changed anything, just rewritten 75 into 25 times 3. And now 25 I know is 5 squared. And then so now this allows me to use the properties that we talked about earlier. I'm going to expand. So now I'm going to expand this into a few different logs, and then I'll be able to use these definitions that were given to us up here. So then, for example, now we'll have 2 log base a of 5. Multiplication means add, so now we add log base a of 3. And now since I know that log base a of 5 was actually 1.3, I can go ahead and substitute that in. And since I know that log base a of 3 was 1.1, we can go ahead and actually get a numerical answer here. So this will be 2.6 plus 1.1, which is 3.7. Okay, so the answer for part A here would be that this value is going to equal 3.7. So all we're doing here is using those same properties we talked about. All right, let's try B. So for B, if I have log base a of 9/5, 9 and 5, 5 is good because I have a 5 up here, but 9 I could write as 3 squared. So this is the same as 3 squared over 5. And then now using the properties, I can say that this is 2 log base a of 3. Division means subtraction, so minus log base a of 5. And now we do the same thing we did earlier. 2 times the log base a of 3, which we knew was 1.1, minus the log base a of 5, which is 1.3. So this is the same as 2.2 minus 1.3, which is 0.9. Okay? Last one, and then we'll move on to the last kind of properties, is C. So for part C, we have, let's say, that was log base A of 125A. We want to try to figure out what that is. 125, I know, is 5 cubed, and I don't know anything about A. But let's just use the properties and see what happens. This exponent goes in front and becomes 3 log base A of 5. Multiplication means addition, so that'll be plus log base A of A. Log base A of 5 was given to us. It was 1.3, so I'll plug that in. And now here, they didn't tell us what log base A of A is, but you should know that this is 1. Because this means A to what power gives us A, right? What power do I take the base and raise it to in order to get this argument in here? Well, the answer is 1, because A to the 1 is A. Okay, so kind of a tricky thing there, but once you see that, you'll be ready for it. So 3 times 1.3 is 3.9 plus 1, so the final answer here is 4.9. Okay? Now, the last section in here is basically using a property that we have not talked about yet, but also one that you've seen before. It's called the change of base property. Which says that the log in any base, let's call it B, of a number A can be changed into a quotient of logs. And you can change it to whatever base you want as long as you keep the new logs in the same base. So I'm going to call this N for new base. And then this A goes in the numerator, and then this B goes in the denominator. Okay, so the change of base property says that log base B of A can also be rewritten in any new base that you want. So typically we're going to use base 10 or base E, since those are the two that are on the calculator. And then you just do it like this. So some easy examples. If I have log base 7 of 8, okay, this can be rewritten in lots of ways. In base 10, we can say that this is equal to log base 10 of 8 divided by log base 10 of 7. If I wanted to use base E, this is the same as log base E of 8 over log base E of 7. So if you type these expressions in the calculator, log of 8 divided by log of 7, we get that this is approximately 1.07. But now if you do log base E, remember that's the same as natural log. So it's natural log of 8 divided by natural log of 7. It's the same exact answer. Okay? So this change of base property works as long as you keep the argument is going to go inside of the log on top, and this base is going to go in the argument of the log on the bottom. But you can change this base to anything, base 10, base E. If you wanted to change it to base pi, you certainly could. But that's the idea behind the change of base formula. Okay, and now the important thing about this is that you can now do lots of different things here as far as solving equations. So for example, let's say we have something like 5 to the 2x plus 1 equals 100. Well, 5 I'm never going to reduce. 100 I can reduce to base 10, but that doesn't reduce to base 5, so I'm stuck. And what do we do when we're stuck? We switch it to log form. So this is log base 5 of 100 equals the exponent, which is 2x plus 1. And now this, we don't have a log base 5 button on the calculator. So what we're going to do is pick one of two. If you want to do base 10, cool. If you want to do natural logs, fine. I'm going to go ahead and use my change of base formula and write this as natural log of 100 over natural log of 5 equals 2x plus 1. Okay. So then now, if I wanted to finish solving, I would have to subtract 1 and then divide by 2. So if I divide by 2, that's the same thing as multiplying by a half, right? So I would say natural log of 100 over 2 natural log of 5 minus 1/2 equals x. This is the exact answer. This is what I would expect to see on a quiz or a test. Either natural log of 100 over 2 natural log of 5 minus 1/2, or if you did log 100 over 2 log 5 minus 1/2, that's also an acceptable exact answer.